to English. We were just chatting a bit because I know Max from his study time. And we're also involved in this circular circuits project. So welcome everyone to this talk in the series of the circular industries talks. And today we have with us Max van Beek, who is a PhD student at TU Delft. And he is involved in the Circular Circuits project, a very large project. I'm sure you're going to say something about it, Max. And his topic today will be reinventing old sorting technologies to avoid future e-waste. And that's a topic that is close to my heart, I should say, because I think that one of the things I often mention when we talk about raw materials, materials needed for the energy transition, things like strategic autonomy, etc. And recycling is, of course, a crucial topic. And it is, since we are switching, let's say, from a system that is focused on the continuous inflow of fossil fuels to fuel our energy system, we are moving away from that towards a system in which we are basically fostering a large stock of metals in society in the form of batteries, solar cells, wind turbines, but of course also all kinds of e-waste. And if we design our product in such a way that they can actually be recycled or reused, that we can extract these materials from it, and it starts with sorting, of course, which makes this recycling a lot easier. Then it would indeed be possible to come close to a circular economy and an energy system based on metals that are continuously recycled. That is the kind of optimum situation that I see as the future. And so I'm really happy that Max is willing to take us with him in his adventures with regards to the sorting technologies of the future. So Max, without further ado, I would like to give you the floor.
Thank you. So yeah, welcome everybody. So as René already said, I'm from TU Delft. I'm from the civil engineering faculty from research and recycling, and I'm one of the 10 PhDs, as we just discussed in Dutch as well, in the circular circuits projects. So well, let's just start. You know, I think like everybody, I got a phone. I think everybody here probably has a phone, but I actually have quite a special phone. It's a Fairphone. A lot of you are probably quite familiar with it, and also what the point is of Fairphone. One of the main goals of the Fairphone is to source their materials sustainably, and of course, as the name implies, fairly as well. However, this can be quite difficult for what are the so-called critical raw materials that are quite often used in all kinds of modern electronics. So, for instance, neodymium magnets are a very famous example, but tantalum capacitors as well. It's very interesting because CRMs are you could probably best see them as kind of the vitamins of the economy. We don't need a lot of them, but we kind of do need them everywhere. Without them, a lot of stuff simply would not work. Furthermore, current supply is quite limited, causing us to be very dependent on a limited amount of countries, such as Congo, China, and Russia, which quite often use quite polluting production methods, and in some cases even have humanitarian concerns. Oops. Therefore, the Netherlands aims to be fully circular and materially independent of primary production by 2050. This will be a very difficult goal, of course, to achieve, but it is something we strive towards. It will probably be quite hard because this graph is a couple of years old, but I think it's still relevant. It shows that the current end-of-life recycling rates are quite low for a lot of materials, especially the more critical raw materials, which you can see here on the left. They're quite often zero or very close to zero. Usually this is due to the fact that their concentrations in end-of-life products, as I said, they're the kind of vitamins. They're very low, which also means that extracting them from these applications is quite often close to impossible. But this is not really the case for electronic components in discarded printed circuit boards, where we can actually find surprisingly high concentrations of these CRMs in different types of components. So for instance, here we have two examples. for instance, for beryllium, almost half of all the beryllium that you can find in a printed circuit board is just located in one type of electronic component. And this electronic component is only 0.29% of the total weight of the whole PCB. So if you just collect these blue capacitors, we already significantly increase the concentration of the beryllium from the printed circuit board. The same goes for magnesium, where actually the vast majority is located in just the heat sinks, which is roughly 7.5% of the total weight. But at the moment, we don't really have any methods to actually separate out these electronic components from each other in order to treat them separately. And thus also, we are not able to extract their CRMs. Luckily enough, the components we have on printed circuit boards tend to be quite standardized due to worldwide manufacturing standards. So it doesn't really matter if you take a component from, for instance, here a DVD player, label maker, or router. In this case, the capacitor on all of these three are basically the same. So we can just combine them together and treat them as the same. Of course, especially in the modern times, a very popular method in this regard is computer vision and AI, where we simply use a camera, a computer, and then separate them out. However, this can be quite limited due to multiple reasons. First of all, quite often it has difficulty recognizing black components, which in the case of a printed circuit board is actually a significant number of them, especially the computer chips, and which contain a lot of valuable materials, for instance, like gold or palladium, that kind of stuff. Secondly, the components can differ quite significantly in size. As you can see here, I mean, just look at them. This is not really, well, it can be quite a big problem for the vision step, but it's especially a problem for actually removing the components from each other, because this is quite often done either through mechanical arms or, for instance, an air spray. And as you can imagine, trying to remove something which is the size and weight of 20 grams requires quite a different approach to something that's less than a gram or even lower than that. So perhaps instead of looking at our futuristic technologies, we should instead be taking a second look in the past. The first one of these technologies is probably one of the oldest separation technologies that we have in history. And I think you're all quite still familiar with it. It's sieving. It's very simple. We just have a sieve and we put the components through it. This is very effective because, as I just mentioned, we have these sub-millimeter sized multi-layer ceramic capacitors, which if you compare it to a computer chip, which is quite often like 1 or maybe even 2 centimeters, and especially if you compare them to very big connecting ports, like the SCART port, which can be up to 10 centimeters, sieving is a very effective method of separating them out from each other. The second machine that we can employ in this regard was actually invented in the late 19th century, so 1890 it's the patent from, and it's called roll sorting. I call it roll sorting, but other names you can find are fruit grader, roller grader, rolling grader. It quite often has to be something with grading or rolling. And as you can imagine, and the name implies, it's quite often used in the food sector. So it's used to separate out different sizes of fruit from each other. But not only that, you can also use it for fish. I found some research done where they used it to separate out seeds, and even one where they do it for spent ammunition, surprisingly enough. So how does the roll sorter work? So it's actually a very simple machine. We just have 2 rollers, which run counterclockwise to each other. And then over the length of the machine, we have a little gap between the 2 rollers, which we increase so we can separate out by thickness. So what you basically do is at the start of the machine, you would have very thin components in this case, so a very thin computer chip. Well, at the end, you will have thicker components. So here can we, for instance, see the result. So it's very effective for these computer chips. The vast majority of the computer chips are located in the very thin part. Well, at the thicker part, so this is in millimeters to be clear, we basically find no computer chips. So just by implementing this machine, so this will be without sieving or anything else, we can already significantly increase the concentration of these computer chips. And also, of course, we also increase the concentration of the other stuff because we separate out computer chips. However, not only can we separate based on shape or size, but we can also separate on composition as well. A classic method in this regard is the ferromagnetic separator, where we simply have an overbelt magnet. So that's the magnet on top, and we feed this machine from the bottom, where the magnetic particles will shoot up and the non-magnetic particles will shoot down. So you have a binary distribution. It's either magnetic or it's non-magnetic. A good example in this regard would be removing iron from copper or iron from plastic, that kind of stuff. However, we have an interesting thing. Because these components are standardized, so they're not random because we don't scrap them, right? We have standardized components. We can actually take advantage of that by angling the magnet inside this machine. We create a gradient, a magnetic strength gradient over the length of the belt, which means that we can have a non-binary but a continuous distribution of ferromagnetic separation. So halfway, for instance, we would mostly have lightly magnetic materials, while at the end strongly magnetic components. Actually, we can show this, of course. So here on the left side, you can see the non-magnetic fraction. So in this case, this would be computer chips, which are quite often, not in all cases, but the majority of the time, they're non-magnetic in nature. Well, in the middle, we could have aluminium capacitors. These are magnetic enough that they do shoot up at the start of the machine, but they drop down halfway because not actually the whole component is magnetic, but only their teeny tiny little connecting legs. And then on the right side, we will actually have the very magnetic components, which in this scenario are the quartz resonators. So effectively, we are able to separate these three components from each other using this new machine. Then another technology which was previously developed in my research group is called magnetic density separation. Here we have an iron oxide particle which is suspended in water. So we would have a ferrofluid, as it's then called. And by placing a magnet underneath this fluid, we create an additional magnetic downward force. This adds to the gravity, artificially increasing the weight of the iron oxide particle, of the ferrofluid, if you will. And because the volume of the particle, of course, does not change, but the weight does, we artificially increase the density of the fluid. And then, as you can probably imagine, depending on the distance to the magnet, the field strength decreases decreases the further away you go from the surface. So this force also decreases, and the density as well decreases. So we can have very effectively a gradient, if you will, in the density of the liquid. So here we can actually see an example. So in this scenario, in this picture, it's good to know that we don't place the magnet underneath the BEV. It's actually angled underneath the BEV. So you have the distribution not in the vertical direction, but in a horizontal direction. You can also see it. So the high density stuff is on the left, while the low density stuff is on the right. So on the left side, you will see very metal-rich components, as I like to call them. So for instance, here we have an aluminium heatsink, but you will also find your computer chips over there and that kind of stuff. Well, on the right side, you will have the lower density liquid, and there's also lower density components, which in this scenario are, once again, these card boards, which mostly contain plastic and very little metal. Thus, if we combine all of these different machines, so sieving, roll sorting, ferromagnetic separation, and magnetic density separation, we can actually quite effectively sort these electronic components by their type, which in turn allows us to create tailored treatment for each of these component types, yielding an effective recovery of the CRMs, and thus promoting their reuse in the Dutch economy and decreasing our dependency on primary production, our negative impacts on the world, and hopefully making every phone completely fair. That was it.
Thank you, Max.
I think it was kind of
thank
short,
you.
but yeah.
Yeah, but thanks for a nice overview. And I'm sure there are many questions, but maybe I can kick it off. Well, a very practical question. You start from having these components separated. How do you actually do that? I mean, do you just melt the solders and have individual components, or how does that work?
Well, there are multiple methods, which you just described is what I do at the moment. So I do it by hand. Luckily, I have some pictures. So I simply have the PCB and I clamp it together. And then I use a heat gun to actually melt the solder. Well, this is, of course, a very labor-intensive process, which you could do in certain countries, but not in Europe, right? That's not going to happen. So there are multiple methods. The simplest method is actually kind of this, but then automated. So they do this in China, for instance, and they have a very big cylindrical drum. And in this drum, they actually have a cylindrical sieve, if you will, and they place the PCBs inside the sieve. So the whole PCB cannot leave, but the holes in the sieve are big enough for the components to leave. Then they just simply spin the drum, and they quite literally put a flamethrower in there to melt the solder, and then the components, because it's rotating around, they shoot off and they fall through the sieve and fall out of the machine. It's not a very subtle way. Another option you have is mechanically removing them, or even dissolving the solder through hydrometallurgy, or dissolving the PCB through hydrometallurgy. That's also possible.
Could you do the heating with induction, or would that also destroy, let's say, the components? And
well, that's always the main question, like how much do you destroy the components? Induction, I think it could be possible. The problem is you really want to focus on the solder joints. Now, I know there's one paper where they tried to do it with infrared radiation, I believe, but that worked quite badly because everything that was black was heating up like crazy. There are some that want to actually use artificial intelligence and a laser to do this, to very specifically target these spots. So you could do it, but it's quite complex, I think. So we're actually trying to see if we can do something which is relatively simple, but it's difficult. So if you have any good ideas, please tell us.
I'm working a lot on magnets, and their induction heating is used very frequently, also because you then demagnetize the magnet, and that is a big advantage. But I can imagine that these components might be too fragile for actually using them. I'm not sure how much. You would need quite a bit of heat, let's say induction heat, because you need to melt the solders, and I'm not sure what then happens to the other components. But interesting, and that's of course a very important first step, because all the other things can only happen once you have the components separated that way.
There are also other methods. There's in the US, there was a company who basically took a reflow oven. I don't know if you know what a reflow oven is, but that's how you make a PCB. So you put the component on the PCB, you put solder paste, and then the component. You put it through a very tight temperature-controlled oven, and then only the solder melts and you're done. And basically what they did is they just had one of these ovens and just put the PCB upside down.
And then they fall off.
And they just fall off. But we actually tried this in the lab as well. I don't think Demo was very happy when they actually found a bunch of components at the bottom. But the problem is these machines are super expensive quite often. They're really expensive machines because they have to have very tight temperature control. And from what I understood, this US-based company, they haven't said anything in recent years. I think the last thing I found was like from 5 years ago. So my guess is they went bankrupt.
Not a good sign.
But but who knows? Who knows?
And one other thing I was thinking is that you describe it, let's say, from the point of view of well, we have all kinds of different separation technologies which we can all use, and if you use them together, you can have, well, this is kind of the maximum separation that you can get now. I could also imagine, and maybe you already did that, or but you just didn't tell it, but I can also imagine that you start from the other way around, that you start from the recycling processes and then say, okay, so which components should I actually separate? For which is separation really important? And for some, it might not be important at all. For some, it might just be they go together in the melter anyways. So why separate them? So is that something that you also did?
So originally, and you can also read this in my master thesis. My master thesis was part of the Peacock project. So circular circuits is an NWO project. So it's by the Dutch government. Peacock is part is an EU project, and there they basically do the same thing, but they only focus on the precious metals. So not the critical materials, but the precious metals. So that's also why you probably saw it in the graphs a little bit, like it's focused on computer chips. Because the precious metals are located in the computer chips. So indeed, over there, basically the only thing we really cared about was getting the computer chips out. Not only the computer chips, but for instance, also this component also contains gold. They have these very teeny tiny little components that quite often contain silver and palladium. So we really focused on those. I'm trying to shift away from that. Actually, this little thing I showed you is a very simplified version of the actual tree, let's call it, or flowchart that I have. It's significantly bigger than this. Because indeed, right now I'm just trying to separate all the components, but trying to focus on very specific components. We do want to do that, but I'm not a hydrometallurgist. So actually, part of our work package is indeed going to measure all the specific material compositions of all of these components, and also have them tell me like what kind of pre-sorting do you want, because there are also cases where the materials might actually on an atomic level might be the same, but one might be an oxide and the other one might not, and I've been told that that's very annoying. if they're mixed together or they have to be treated differently, that kind of stuff. So.
Yeah. I've also visited Umicore at some point, maybe others did as well, and then you can also hear the stories about some separations are crucially important. For example, you want to get the aluminum out because that destroys all your hydrometallurgical processes that they have. So some things are really sensitive, and other things are, well, doesn't matter. You just throw it together anyways. So that's interesting. So it's really also a systems approach in the sense that in the end, you're kind of envisioning a system that extracts as much material as possible, let's say, in a reasonable economic fashion, I guess. So
and we also hope that by separating out these different components, a lot of stuff actually switches from being a waste or a pollutant to actually being a valuable thing. So this aluminium, which you just talked about, you mostly find it in the aluminium heat sinks, of course. I showed there's magnesium in there, but the vast majority is aluminium, which is a huge pollutant. But what if I just tell you that I just have a bucket which only contains aluminium heat sinks? Then suddenly it's not a dirty pollutant, but it's arguably an aluminium source. I mean, compared to like a bike, it's nothing.
No, of course, right? But
like
still,
it's very little compared to other places because it's a major metal. But still, suddenly you go from an arguably negative value feed to a positive value feed, which actually also hopefully, let's hope, that's what our hope is, actually make this whole thing feasible. Because that's the main issue. Quite often we can actually extract all of these metals from a technical perspective, but not from an economical perspective. So by trying to do very simple pre-sorting methods, we hope we can increase the concentration quite significantly, that it hopefully also becomes economically feasible.
Yeah, very nice. I'm just looking, I don't see any virtual hands raised, but if you have any questions, please either raise a virtual hand or open your mic. Jaco. You're muted still. Sorry.
Still. Yeah, thanks for, well, hi René, hi Max. Thanks for a very interesting presentation, shedding quite some light. What I didn't really get from you, well, it's a very nice overview, but I did, could you say a little bit more to what extent, say, these practices are already there? Because in the end, what you say, this is bringing that in shouldn't be rocket science. Say the methods, the principles are there, it's just getting it in. So there must be all kinds of barriers why it doesn't happen or hasn't happened. So could you say something about the current state of this kind of techniques of separation, and also what is actually preventing from getting them into the end of life process much better than currently probably will be?
Yeah, so at the moment, they sort of do it. But they quite often don't use machines to separate out components. But for instance, if you go to the Umicore website, so that's the metallurgical recycler, they actually, you can either deliver them printed circuit boards or CPUs. They actually accept CPUs separately. So you will see that some companies, they manually remove the CPUs from their PCBs to send them in separately because of this increased concentration. You will even find some weird YouTubers, usually they're kind of like Australian or American rednecks, that simply do it in their backyard and extract these materials. But for the more automated way, there isn't really a lot being done right now. So I know there is a company which sells these depopulating machines with the metal drums and the flamethrower I talked about. They also sell a sieving machine. I've seen some videos from an Italian company which also claims to be doing it, but I could not. When we asked them, they didn't really provide any evidence, or they didn't want to work together with us. So not sure, we couldn't see it. So it will be indeed quite a big difference. And this is also one of the dangers, because it probably only works if everything kind of works. There aren't really a lot of in-between steps, I think. Or you can do you can have it with in-between steps, but then you would have the danger of cherry picking. So you would only have the chips taken out. So you would only sort for the chips because that's where the gold is located, and all the rest you kind of ignore. So that's an in-between step you could have, I suppose. But yeah, it's kind of. Yeah.
And say just an how far is a company like Umicore on this? If they are specializing in handling motherboards or CPUs?
So Umicore works with a very big pyrometallurgical process. So from what I understand, they actually want as little pre-processing as possible. Because one of the main reasons, because it's pyrometallurgical, it requires a lot of energy. So they actually burn the plastic that's in a PCB. So both in the actual PCB, but also in the components. And actually, when we went to visit them, they actually told us that they prefer that people do not remove these plastics, because otherwise they would have to use coal or gas or oil to actually heat up this process. So from a pyrometallurgical perspective, it would actually be disadvantageous to do this unless you really increase the concentration, which is also one of the reasons why we kind of want to switch to a hydrometallurgical processing, because it requires significantly less energy. It can also be more complicated because you have to deal with liquids and acids. But then you don't really have that issue of the plastics being required. But it's probably going to be a topic for like in half a year, because then I think Fabian, our hydrometallurgical guy, is going to present, I have to guess.
And say what is preventing us that this is diffusing or developing more quickly than it is now? What are then the issues?
Interest, and money. I think the main issue is money, as in most cases. Because I said, like the CPU removal thing that is happening. So that's also one of the main goals that we want, is to actually make sure that you don't really have any waste, but that everything is valuable on its own as well. So you avoid this cherry picking problem. There have been some projects in the past where I tried something similar. In literature, it's actually very interesting because in literature, you quite often hear it described as we need to depopulate the PCB, sort the components, and then do hydrometallurgy to recover the materials. There are a decent amount of papers on the depopulation step. There's 2 papers in total on sorting, of which one mentions it offhand and isn't really about the topic at all. And then a couple on the hydrometallurgical step. But there's actually nothing done in this middle step. And quite often they aim for very expensive methods. So it's also, all of these methods I try to employ are very cheap, both in capital cost, but also operating costs to decrease overall price. That's the hope. Does that answer the question?
Well, quite a bit. Thanks for that.
I saw something in the chat.
Yeah, there's much more to ask or to continue, but there might be other questions as well. It's very helpful and interesting. Thank you.
Indeed, a question in the chat about what advice you would have for the province to take up some of these methods.
The province. Well, the province is a tricky thing in electronics because quite often you need to, if you want to make real change, you need to think bigger than a province. I think on a provincial and municipal level, the most important thing is actually collecting these electronics, because right now the collection of e-waste in the Netherlands, I believe, is around 50%, which is quite low. Because in the end, you can only run this process if you have enough volume. If we treat 10 PCBs per day, it will never be profitable or getting anywhere close. But if we have tons of them, you can run them. So that's also, I suspect that you will not have a lot of these plants in the Netherlands, maybe 1, maybe 2, which is also an advantage, but also increases transport. Any risk? I think this can be quite cheap and simple to implement. The bigger risk is probably anything liquid related. I know, so the magnetic density sorter, we recently had a new test setup. So this one, which we made together with one of our project partners, mine, previously known as Reukema, in Harderwijk. And they want to move this machine later to them, and actually place 5 of them, I think, parallel to each other, to separate brass. But he mentioned that the permitting takes a long time. Basically, this machine got placed here, and he was like, well, you're probably going to have it for the next 1 or 2 years. But then if we wanted to later move to us, we already have to start the permitting process already. There's actually a thing I've noticed, and probably the other circular structure PhDs can confirm, is that a lot of the companies are talking a lot about bureaucratic red tape.
Yeah.
But as I said, mostly above the provincial level. That's the main issue, I think. Yeah.
What is the liquid that is used here? Because I guess that's the culprit.
Oh, the black stuff is ferrofluid.
Yeah.
So those are the iron oxide particles.
Okay. And because I'm wondering why the permitting is, why the permitting is such an issue. Is that because of the liquids? Is it because it doesn't seem to be a machine that uses a lot of heat waste, or the waste?
Whenever you deal with waste, it becomes very complex. I don't know about e-waste yet, but I know that when we went to MyRec, they had really big problems, mostly due to batteries. Yeah. I remember them casually telling us that they had, I think, like a small fire every week.
Yeah.
Because because right now what they quite often do, they don't do this, right? They either throw the whole PCB in, as I call it, the oven, so they send the whole PCB directly to Umicore. Yeah. Or what they do at MyRec and some other places, they first shred the PCB to teeny tiny little pieces, and then they quite often use mechanical separation methods and then also vision and sensor-based sorting to separate out as best as they can. But which works quite well from what I've been told. but it still leaves the concentration of these critical materials too low. So that's why we want to sort on component level first. After sorting on component level, you probably still have to shred them and then still do ferromagnetic separation to actually further increase the concentration. But I know it's mostly the batteries that causing. I believe that's also one of the main reasons that the EU recently changed the battery regulations, right? That you have to be able to find batteries.
And that the fire hazard is of course extremely high, and you can see that now in all these recycling plants that they're struggling with this. I've also visited A&M Recycling, and they indeed manually separate the processors, but also the memory chips and some other components. So they do a couple of first steps.
Gold containing components. They remove the gold containing components.
Yeah, basically. And of course, if you want to take it steps further, you could start to shredder stuff. Then also this fire hazard. I mean, if there's only one battery, it could already start a fire, basically. So I can see that that's an issue. I see, Jaco, you have your hand raised.
Yeah, I wanted to continue on the point, the question by the province. So I fully understand that it's a matter of scale and economies of scale to get it implemented or feasible. But of course, provinces can be important in the earlier experimentation phase. And indeed, it's not only to the permitting, but not every site of every business park is they have categories of that and the kind of waste or they can handle. So there is also a spatial aspect to that where you can do that in addition to the permitting, and it can be quite nice or efficient to have that kind of governments also in an earlier phase involved, and not only when you are scale up, but that it gets somewhere earlier in the planning cycle.
Sure, you want to respond, Max? But
I think that was mostly an answer to Annelies, right?
Right, indeed. And Annelies says thank you. So that's good. And we also have in the chat, we have a question by Ryan Bark. Would you consider building different business cases needed to scale into your research? As you say, this is of such importance to any recycling technology being successful.
Well, that's, I think, a spoiler for in a couple of weeks. Because one of my colleagues, Maiwi from Erasmus University, I think is going to talk about business cases.
Okay.
So what I can answer for our part is that the way we imagine it is actually, and then I have another slide for that. Woo, so this is the main plan of my work package. So my project is specifically going from the components and pre-sorting them using mechanical means. So we already have the PCB boards depopulated, because the depopulation of PCBs is actually outside of the scope of circular circuits. Depopulating them, and this will be a bulk process. So this will be continuous, going, very simple, easy machines. And then Saxion Hogeschool, together with some help from TNO, is actually going to help develop a vision-based or sensor-based software, I should say, which actually separates out these already pre-sorted components. So we go from like this mixture to like this mixture, and then they actually go from this mixture to this. But they want to do it in a different way than is currently being done. So right now, basically the recycler produces a material and then it tries to sell it to the market. And the idea of this is actually going to be that this will be recycling on demand, as my supervisor Peter Remmel likes to call it, where the consumer, so the final consumer, actually tells this sensor-based machine, I want neodymium. And then the sensor-based machine will take from these pre-processed buckets, or bins, if you want to call them, that I made with the continuous machine, takes out all the components which contain the neodymium. And then in turn, they will be processed using hydrometallurgy, of course, to actually get those materials out. So that is a different business case than that we're currently imagining. So not going basically from, I have a waste, I make this out of it, I try to sell this to the market, but I have this, I try to pre-sort stuff to useful bins, and then the market says I want this, and then actually create that in the last step. So that is a different business case, I think. That answers one of the parts. Yeah. There will be more business case, but as I said, that's I think in a couple of weeks. Yeah.
Yeah. Thank
Any
you.
other questions?
I don't see any other questions. Any questions? Not anymore. I don't see any hands raised. So I guess we are done. So yeah, thank you, Max. I find this very interesting. I think it's also a very valuable topic and a very useful topic to look into. More and more of this will be needed, and it's all now about, I think, using smart technologies to make this economically feasible in countries like the Netherlands or other European countries, because I think it would be great if we could, well, take care of our own waste, not only because, well, it's something that we need to do, but also to prevent these flows going to other parts of the world where technologies and regulations are not as strict as they are here, which can cause all kinds of really dramatic pollution issues. So that's also a reason why we should do that. And also because of our own strategic autonomy with regards to these materials, I think it is crucial that we have technologies in-house that are feasible, that are doable, that are clean, that are economic to actually extract these materials again. Well, thanks for your presentation, Max. Thanks for the work, and like you said, we will be seeing more from the Circular Circuits project in the near future in this series. So thank you for now, and thank you all for listening in, and see you next time.
Thank you. And
Bye-bye.
if anybody has any other
Yep.
questions, you can find my email. Just email me.
Yes.
mc.vanbeek. m.c.vanbeek@TU.nl. Ik kan also find me on TU Delft.
Yeah.
Yes, there is a
Okay.
Circular Circuits website. It's quite literally, I think, circularcircuits.nl.
Okay. Cool. Okay. Bye-bye.